Hi, everyone. Let's finish our discussion about aromatic molecules, specifically what makes molecules aromatic, the special stability that some molecules possess. Yeah, so nature, she makes all the rules, right? And so we're trying to figure out these rules. So let's continue with key concepts, Unit 1, Part 2. We might call this Part 2B, right? So there's another video called Aromaticity, and that went over Unit 1, Part 2, the first half or so. And it began looking like this. So if you will, you probably should open this up and take notes, either type on the screen or whatever works for you so you can remember and understand this material. Okay, so last video on aromaticity, first we entered the idea that, hey, not all molecules are created equally. Nature has some favorites. Molecules that are aromatic have this special or unusual stability. And the source of that special stability is that the pi electrons are delocalized. Fancy talk for saying, hey, these pi electrons that other reagents want to react with, they're just flying willy-nilly all over the ring. They're hard to pin down. They're not localized at one spot. They're spinning all over the place. That makes it difficult for reagents to react with them. And if they don't react, the molecule is stable. Okay. So there's a whole video about that and how to predict it, right? There's 4 criteria. You have to, this is worth writing down. What you want to do in order to identify aromatic molecules is first see if they are cyclic. And it doesn't mean the entire molecule is just one ring. It just means somewhere in the molecule there is a ring. Okay, and then focus your attention at that ring and decide as best you can if the ring is flat or planar. Third, see if all the atoms in that ring have a p orbital where these pi electrons can fly around. We said that all the atoms in the ring are conjugated. And what that really means is a p orbital on every atom of the ring. So in this cyclic portion of the molecule, which has to be flat, every atom has to have a p orbital. Why? Because you need a Huckel number, a special number of pi electrons to be able to fly through anywhere above and below the plane of that ring in these p orbitals. Remember orbitals? I think of them as like parking lots for electrons, or maybe a better analogy would be like flight patterns of electrons. Like, airplanes have to maintain a certain flight. If they're in a holding pattern over an airport and the air traffic controllers are saying, okay, this plane, you're in this flight pattern, you're in this other one. Hey, let's make sure you guys don't collide. These regions above the airport where the airplanes fly without colliding with other airplanes, that's analogous to electrons in atoms or electrons in molecules. They exist in these orbitals, these regions of space above and below the plane of the molecule where the electrons can be found. And they're orbiting in such a way, moving in such a way that they shouldn't collide. Huckel number of pi electrons, and those special numbers, nature decreed them, 2, and then add 4 to every one of these. So 6, 10, 14, 18, and so on. 22. Yeah. Those are the numbers of electrons that make a molecule aromatic as long as the other 3 criteria are satisfied. Cool. Okay, on with the show. The last video only discussed molecules containing carbon. Well, carbon and hydrogen. Aromatic molecules can have elements in addition to carbon and hydrogen. For example, nitrogen, or oxygen, or phosphorus, or sulfur. These atoms could be part of the ring. Okay, and new idea, gets a new word, new definition. The word for that is heterocycles. Heterocycles just means cyclic compounds with rings, where the ring atoms are something other than just carbon. So pyridine, hey, that was a reagent in some of our reactions last semester. Yeah, Pyridine is actually an aromatic molecule. There's 6 atoms in the ring, but not 6 carbon atoms. One of the carbons has been substituted with a nitrogen. And turns out it is aromatic. Let me see if I'm skipping anything. Right here. Nature prefers to make stable compounds. So, yeah. Right. So, just a quick little intermission here. One of the tasks students have to do is identify aromatic molecules. And we all love shortcuts. We do. Unfortunately, some students create shortcuts that don't always work. They work in some cases, they don't work in every case. Okay, so you gotta be a little careful with those. So I'll do the best I can to give you shortcuts, but don't shorten up any more than what I give you. You can redefine them as we go. I'll try and make that a little more clear. Here we go. Okay, so sample problem. Are these molecules aromatic? Well, let's find out. Check and see if they're cyclic, planar, conjugated, and a Huckel number. Huckel, however that name is pronounced. Okay, so pyridine, is it? Well, I can already say it was. But let's pretend we didn't know. Okay, is it a ring? Sure, a ring of 6 atoms right here. Is it flat? Okay, so flat, you really want to avoid sp3 hybridization. Hybridization, remember, that determines the shapes above an atom, about an atom. sp3 is tetrahedral. So if you have a whole bunch of sp3 hybridized atoms together, it's unlikely to be flat. sp2, however, the definition of the geometry, the shape about an sp2 hybridized atom is trigonal planar. Yes, it's flat. And an sp hybridized atom should be linear. Lines are flat too. Yeah, so I want to avoid sp3. So anybody sp3 here? Okay, that's the answer is no. How would you know? Well, what you can do, let's start with a carbon atom here. Carbon bonds 4 times. I only see 3 lines. So where's the missing bond? It's the hydrogen. Okay, 3 bonds to carbon. One of them is a double bond. So going back to Gen Chem, and last semester we reviewed this too. A double bond consists of a sigma bond and a pi bond. And I'm arbitrarily picking one line to be pi. It could be the other one. But pi bonds come about from p orbitals overlapping. Okay, and the main idea here is for this carbon, this one right here, to make a pi bond, it needs a p orbital. And elements in the 3rd row, or actually all the elements, yeah, all the elements, they only get 3 p orbitals, right? So you remember, gosh, going way back when, back to Gen Chem, said, hey, draw the atomic orbitals for carbon. And you'd say, okay, there's a 1s orbital, there's a 2s orbital, and then there are 3, there they are, 3 p orbitals. Okay, and then we're saying, hey, in order to make a pi bond, you got to keep one of those p orbitals for the pi bond. And that leaves the other orbitals for hybridization. So this atom is making a pi bond. So take away one of the p's to make that pi bond. And then it's left with an s and 2 p's. An s and 2 p's, that's sp2. There you go. So this carbon's sp2. This carbon's making a pi bond, sp2. This carbon's, every carbon is making 1 pi bond. So it's sp2. And how about the nitrogen? I got a single bond on its left side and a double bond on its right. Pi bond needs a p orbital. So nitrogen, you have to use a p orbital to make the pi bond, leaving you with an s and 2 p's. Yeah, the nitrogen is sp2. Okay, and then it has a pi bond to the nitrogen. So we already can count the pi electrons of this pi bond. There's 2 of them here, right? Back when we were drawing Lewis dot structures, we said 1 line equals 2 dots, right? 1 covalent bond results from 2 shared electrons. Yeah, so a pi bond is 2 electrons in it. This pi bond on the left has another 2. This bottom right pi bond has another 2. There's a total of 6 pi electrons. And so it does have a Huckel number. Oh, I skipped conjugate. Every atom is sp2, meaning it has a p orbital, right? sp2, 1 p orbital left over for those pi bonds. Everybody has a p orbital, so yes, everybody's conjugated. And if they're all sp2, it should be planar, and it's cyclic, so yes, aromatic. What about this lone pair? What does this have? This lone pair is not part of the pi system. Yeah, it's not in a pi bond, not in the double bond. But there's more than that. We'll get to that right over here in the second example. For now, though, it is a fair question in Gen Chem. I don't think I'll ask an organic, but as a review, I guess I can. What orbital do these electrons sit in, right? An orbital is just a parking lot. Flight pattern for these flying electrons. So where is it? Well, this nitrogen is sp2 hybridized, and it has a pi bond. So this pi bond has 2 electrons. It's shared with nitrogen. They're in a p orbital. The sigma bond, this nitrogen is making a single bond to the carbon as well as the double bond. The sigma bond, though, is an sp2 hybridized orbital. The single bond on the left side is also sp2. And in fact, the lone pair is also sitting in an sp2 hybridized orbital. Cool. Okay, we're done with purity. But let's look at parole. Okay. Gonna ask the question, is it cyclic? Is it planar? Is it conjugated? Does it have a Huckel number? If it has all 4, it's aromatic. If it doesn't have all 4, we're just going to classify it as non-aromatic. We're not going to worry about anti-aromaticity for the exam. Okay, so is it cyclic? Yeah, it's a ring of 5 atoms. It's got a ring, doesn't have to be 6. There's a ring. Good, check. Is it planar? Well, the 4 carbon atoms, what's their hybridization? Well, this carbon's making 1 pi bond and a bunch of sigma bonds. I see all 4 bonds here. That's a single, and then there's a sigma and a pi. Yeah, 1 pi bond needs a p orbital, so this is sp2. And it's true for all 4 carbons in this ring. Nitrogen, let me slow down, sorry. Every carbon is sp2. So every carbon being sp2 is flat. If the molecule wants to be aromatic, it will let all 4 carbons be flat together. So this part of the molecule is flat. Let's take a piece of paper. And there's 4 corners to this, right? So let's let this be the bottom half of the molecule. So there's 4 carbons, back to the screen here. There's 4 carbons in this ring. So let them, I know it's not a square or rectangle, but pretend it is. The idea is when you attach the nitrogen to the top of those 4 carbons, if you do it sideways, you can attach it out of plane if you want, but you could also attach it in plane, even if the atom is sp3 hybridized, even if it's tetrahedral. So that's something you have to look out for. Nature is a little, the rules are not very rigid when it comes to planar, predicting whether a molecule is flat or planar. Nature, she makes the rules, and we haven't quite figured it out. All I'm saying is we have to allow a little flexibility. So looking at nitrogen, and only nitrogen, and don't even think about aromaticity, what would you predict the hybridization to be? Well, nitrogen, what are you doing? You're making a bond to hydrogen, single bond to carbon on the left, and a single bond to carbon on the right, and you have a lone pair. You have 3 bonds and a lone pair. You need 4 orbitals, 1 for each of those sets of electrons. You got a single bond that needs an orbital, another single bond, and another single bond, and a lone pair. You need 4 orbitals. And then to make a a hybridized system, you need an S, a P, and a P. 3 Ps and an S, your sp3 hybridized nitrogen. That's our prediction. And it's true for ammonia. NH3 structure would look like that, has 3 single bonds, a lone pair. It is true that ammonia, NH3, is sp3. So I would expect this nitrogen, it's also making 3 single bonds, a lone pair. It should also be sp3. Tetrahedral shape. And now what I'm saying is, even though it's tetrahedral, you can attach this nitrogen to the flat part of the rest of the ring in such a way that it still will remain flat, even though it's sp3. So, shortcut, if you have one atom that's sp3, it may still be planar. It's not enough to say, nope, can't be aromatic. Maybe it is. Be a little flexible. 2 or more odds are probably no, it's probably not going to be aromatic. But again, don't let it be the guiding factor. Look and see if something else doesn't work. Because there's 4 things that must fit. Okay. But let's say that this is sp3 and we could attach it to the ring such that the molecule still is flat. So we're going to say, yeah, it looks like it could be flat. You can put a little maybe, because nitrogen is sp3. So maybe not. Maybe. Conjugate. Okay, now this one I would have thought was a clear, no hands down, we can figure this out. Nature, though, she likes to bend the rules. Okay, the carbon, you're making a pi bond. I see the pi bond, the double bond. You have a p orbital to do that. So is the other carbon. These 2 carbons are double bonded together. They must have a p orbital too to make that double bond. So all the carbons have a p orbital. If nitrogen has a p orbital, then we could say it's conjugated. But we just said nitrogen's sp3. It doesn't have any extra p orbitals. All the p orbitals got used up to make sp3. So I would have said, no, it's not conjugated. The problem is you go in the lab, do studies, do tests. It's really, really stable. There's another test you'll see at the end of the video we can do, and it also holds up to that test. Turns out pyrrole, this molecule, is aromatic. And now we're left to explain it. Well, the explanation is Mother Nature said, I like things to be stable. And I know I normally make an atom with 3 bonds and a lone pair, sp3, but I make all the rules. Mother Nature says, let's move that lone pair into a p orbital and make the atom sp2. Let's rehybridize it so it's sp2. Bending the rules here. But if you bend the rules, you got to stick with it. So if you're sp2, now you have a p orbital. That's a parking lot for some electrons. Mother Nature says, yeah, I choose the lone pair to go into the p orbital. Okay, and then she gets conjugation. Every atom now has a p orbital. However, if you move it into a p, Mother Nature, you have to count it as pi electrons. They're in the p orbital. And she says, that's what I wanted to do, because there's a pi bond here and a pi bond there. There's already 2 pi bonds in the molecule. I write it over here because I really marked up the screen. Pi bond there, pi bond there. So that's 2, 4. 4 electrons is not a Huckel number. But if you count the lone pair, 2 more, you get 6 pi electrons. Hey, that is a Huckel number. And now it's aromatic. And now nature will say, yeah, nitrogen is now sp2. So we're definitely planar. Okay, so that's tricky. For those of you who like memorizing ideas, if an atom, sometimes it's nitrogen, sometimes it's another element. If you see an atom making 3 bonds in a lone pair, it looks to be sp3, and it's the only atom in the ring that's doing that, Mother Nature might say, maybe I'll make it sp2 and see if I can count that lone pair as part of the pi electrons, try and get to a Huckel number. And I just misspoke. Sometimes more than one atom can do this. Mother Nature, she makes the rules. Okay, so it's sort of like a wild card. Think of that lone pair as a wild card, as long as the nitrogen's not already committed that p orbital. So in pyridine, Nitrogen has a lone pair. That's not a wild card because nitrogen is already using a p orbital to make the double bond. You already have a p orbital in play. You can't get another one in there. You only get one per atom. So lone pair can't get into that p orbital. And then Mother Nature says, yeah, I don't want it to, because this molecule has a pi bond here, another one there, another one there. That's 6 pi electrons. I do not want to count the lone pair. That would be 8, which is not a Huckel number. Okay, here we go with furan. Same deal here. Is it cyclic, planar, conjugated? Handwriting's getting worse, sorry. Is it, does it have a Huckel number? Okay, does it have a ring? Yeah, I see the ring of 5. Planar, maybe. 4 carbons are definitely sp2. The oxygen is sp3. It doesn't have 3 lone pairs. I'm sorry, it has 2 lone pairs and 2 bonds, not like nitrogen, but you'd still say it's sp3, right? It's got a single bond, 2 lone pairs. That's 4 pairs of electrons, right? 1 line equals 2 dots. A single bond has 2 electrons in it. So this oxygen has an octet, 8 electrons, 4 pairs. Each pair gets an orbital. Need an S, a P, and a P for sp3. That's a prediction. But now think of one of those lone pairs as a wild card. And that's what nature's going to do. She's going to say, yeah, oxygen, why don't you go sp2 like nitrogen did? So that one lone pair can go into a p orbital. And now we're definitely flat. If every atom can get sp2, it's flat. Planar, check. Conjugated, hey, well, it's sp2. It has a p orbital, oxygen does, as do the other carbons. So yeah, it's conjugated. Huckel number, yeah, I got a pi bond here for 2 electrons, second pi bond for 4, and I get to count the lone pair that's sitting in that p orbital as pi electrons. We have 6. It does have a Huckel number. Okay, so back to the middle example. Here's the orbital diagram. Every atom has a p orbital. We color code the top lobe of the p orbital red, the bottom one's blue, but it's all one orbital, right? And in this molecule, pyrrole, nitrogen puts a lone pair into the p orbital. That counts as 2. And then the carbon-carbon double bonds, each carbon has a p orbital with 1 electron in it. Yeah, for a total of 6. And then this diagram's not entirely accurate. All the lobes of the p orbitals should touch. They overlap, which means that this 1 electron here is free to roam anywhere, as are the other 6 electrons. And they can go in the bottom lobes too. Anywhere they want to go. Trick question, but I think we can answer it. Imidazole. I know, you don't have to memorize these common names. Yeah, for the L1 pyrrole, pyridine. Pyridine, you do need to know. That was one of the things we asked students to memorize last semester as one of the reagents. So we're going to keep using pyridine. But the other ones, no. You don't have to memorize their names or their structures. No. Okay, imidazole. This molecule with a ring of 5 atoms, 2 of them nitrogen. Is this aromatic? Well, let's go around the ring and find, let's go around and check our criteria. Is it cyclic? Is it planar? Is it conjugated? Does it have a Huckel number? Okay, cyclic. Yeah, it's a ring of 5 atoms. Planar. Well, carbons are all sp2 hybridized. They're all involved in double bonding. So is this nitrogen with the 3 next to it. This nitrogen has a double bond. It is most definitely sp2. It's got a pi bond. It's using a p orbital. Yeah, it's sp2. sp2 is trigonal planar, flat triangle. So nitrogen's definitely flat here, as are the other carbons. This other nitrogen, if I wasn't thinking aromaticity, I would say, hey, nitrogen 3 bonds, lone pair, you should be sp3. That still could be planar. But now, wait, that might be a wild card. this nitrogen could use its lone pair to count as pi electrons if it becomes sp2. So the nitrogen here is probably going to go sp2 and put that lone pair into the p orbital so that it counts. Okay, is it conjugated? Well, the top nitrogen definitely has a p orbital because it's making a pi bond, a double bond. And now we're going to play the wild card on the second nitrogen and say, hey, lone pair, go into that p orbital, rehybridize, don't be sp3, be sp2. And now every atom in the ring has a p orbital. It's conjugated. Do we have a Huckel number of pi electrons? Well, one pi bond is 2 electrons. Second pi bond is 4. Lone pair counts, that's 6 pi electrons. Yep, it's conjugated. Now, how come it's this lone pair on the bottom and not the lone pair on the top? And that's because this nitrogen is already double bonded. It already is using its p orbital to make that double bond, the pi bond. So it can't use the lone pair. Remember, one orbital can only hold a maximum of 2 electrons. You can't squeeze the lone pair in with the double bond. No, 4 electrons in one orbital, nope. Nature doesn't allow it. She can't break that rule either. Okay, cool. Okay, so that's the main idea. I should have had some counterexamples because not every atom with 3 bonds and a lone pair will hybridize sp2, right? Anyways, in the homework, we'll see some counterexamples. But it's a wild card. So if nature says, yeah, if I can get the atom to be sp2 and at the same time count the lone pair as another 2 pi electrons, if that gets me to a Huckel number and it's cyclic, planar, and conjugated, then winner, it's aromatic and a much stable molecule. New idea, something to look out for on exams. I'll try and clue you in. I'll say, hey, this is a weird reaction. Oh, something unusual is happening here. Please explain. Okay, so you'll be clued in the fact that it's weird, it's unusual, it's surprising. What's this chapter about? Aromaticity. So you'll have to make the connection there. Something weird, something unusual is happening. Aromaticity might explain it. Is it cyclic? Is it planar? Is it conjugated? It does have a Huckel number. Okay, what are we talking about by surprising or unusual reactions? Well, what's not surprising, I hope, is if you take an alkane, cyclopentane, mixed with sodium hydroxide, nothing happens. Sodium hydroxide is a strong base, and carbon with hydrogens is not an acid. There are hydrogens present, right? Every carbon has 2 attached hydrogens, but these hydrogens are not acidic. They don't fall off and put a negative charge and a lone pair on the carbon. Why not? Carbon is not very electronegative. It's not electronegative. It can't stabilize a negative charge, so it does not want a lone pair. Chlorine, though, is electronegative. Fluorine is electronegative, so it likes having a negative charge. Oxygen is somewhat it's fairly electronegative, so negative oxygen is stabilizing, right? Just like in sodium hydroxide here. There we go, there's a little set structure of sodium hydroxide. Oxygen can stabilize a negative charge because of its electronegativity, but not carbon. So it's not surprising that there's no reaction. And hey, if it's an alkane, no reaction. If it's an alkene, still should be no reaction. No, that's true. Well, hey, wait, this molecule, is it aromatic? Is this molecule aromatic? No. That carbon is, well, let's go through the criteria. Sorry. Is it cyclic? Yes. Is it planar? Well, 4 carbons of this molecule are sp2. They're definitely flat. This one has 2 hydrogens. It is definitely sp3. No wild card here. There's no lone pair. This is sp3. But remember, you can connect an sp3 atom to a flat part molecule in such a way that it could still be flat. So it's a maybe. It's not enough to say, no, not aromatic. You need more evidence. So let's go after some conjugated. Aha! Does everybody have a p orbital? No, this top carbon does not have a p orbital. There you go. So it's not conjugated. So it's not aromatic. Someone else might say, yeah, but what about, why don't we just check the Huckel number? And yeah, you could have done that too. How many pi electrons are here? There's 4 pi electrons. There's 2 double bond, 1 line equals 2 dots, 2 electrons here, 2 electrons there for a total of 4 pi electrons. 4 is not a Huckel number. Yeah. Okay, so it's not aromatic. Why is this not very special molecule? It's non-aromatic, just normal. These are all non-aromatic molecules, the 3 on the screen. Even sodium hydroxide is non-aromatic. Everybody's non-aromatic. But wait, why did this react? What? Well, when we went through the process of finding out whether or not this is aromatic, we discovered the problem. It's sp3 on top. But remember, nature likes aromaticity. She likes to bend the rules. Carbon, you shouldn't be acidic with hydrogen. Mother Nature says, but wait, what if it did? What if hydroxide ion would be allowed, Mother Nature says, to grab this hydrogen? Then these electrons would become a lone pair on the carbon and be negative. And then you're saying, oh my gosh, wait, Dennis, you just said the carbon's not electronegative. It can't stabilize that negative charge. And you're right, it's still true. But wait, it's going to get some help. Is this product aromatic? Well, is it cyclic? Yeah. Is it planar? Well, I got this atom here that has 1 hydrogen, 3 bonds, and a lone pair. Just like nitrogen did. That lone pair is now a wild card. We can put a maybe here, but you know what? Nature says this reaction goes forward where most of the time we would say, carbon's not an acid. It shouldn't work. Why is it working here? That's so unusual, surprising. Unusual, what? Yeah, because aromaticity is involved. So nature is allowing this to become sp2. That's a yes. This is going to play the wild card and put the lone pair into a p orbital. Lone pair and the p orbital. And now every atom has a p orbital. And you count that lone pair. So how many pi electrons? Sorry, I'm jumping the gun. It's too excited. Conjugated. Yes, if this top atom, after losing a hydrogen, which now has a lone pair, puts that lone pair into a p orbital, it'll go sp2 with a p orbital. That becomes conjugated. And the Huckel number, yeah, we got 6 now because the lone pair is going to have to count. We got 6 pi electrons, so that's a yes. Product is aromatic. That gives it special stability, and that stability can help counter the negatives. Is that a good way of saying it? The instability? That's a better way. The instability of having carbon with negative charge. Also, where are these 2 electrons? Are they localized on this top carbon? No. Aromaticity means all pi electrons are free to roam anywhere. So sometimes this carbon on the left has the negative charge. Sometimes the one on the right, on the bottom, over here. Those 6 electrons are flying around the ring. No one carbon is trying to stabilize the full negative charge. All 5 atoms of carbon in that ring are helping to stabilize this extra negative charge. Mother Nature says, looks good to me. And it turns out it's true. It's actually a quite stable molecule. Not as stable as benzene, because it does have a negative charge, but it's stable enough to exist. Whereas the reaction between cyclopentane and cyclopentene with hydroxide, that product doesn't exist. It doesn't react. This one does. Aromaticity. There'll be other homework problems that'll exploit this. So watch out for homework problems say, please explain the unusual reactivity here. You'll look at the reaction saying, we never studied this. What the heck is this all about? Just like this one. Alkanes don't react to hydroxide. Never saw that before. Okay, think aromaticity. See if the product is aromatic. Okay, something got chopped off here. Great, we're recording. We'll make this work. Okay, the last topic is polycyclic molecules. Let's see if I can just go to that. New share. Let's actually go to the key concepts. Did I keep it open? I did. Yay. Okay, here we go. Hopefully you can see the screen. And I get to highlight it too. Polycyclic aromatic molecules. Those are molecules that are aromatic. More than one ring. Poly means many. Cyclic means ring. So polycyclic, polycyclic maybe, means molecules with more than one ring. Let's go back to here. Okay, so if you have this molecule on the exam and I ask, hey, is this molecule aromatic? If there's more than one ring, all you have to do is find one ring that satisfies the criteria. Is it cyclic? Is it planar? Is that one ring conjugated? And does that one ring have a Huckel number of pi electrons? Okay, and then you got to be creative, kind of open your horizons here. Let me ask the question. This molecule is called pyrene. How many rings are here? There are more than 4, right? So yeah, I see the 4 hexagons, that's 4 rings, but you can go around the entire perimeter. That is a ring. You can go around 3 of these. That's a ring. You can go around 2 of them. That's a ring. There are lots and lots of rings. And your job is to find one ring out of all those possibilities that satisfies all 4 criteria. You only have to find one. And then we will say, yes, it's aromatic. That's how the game's played on the exam. Cool? All right, let's play the game. And you want shortcuts? Well, look at these 4 hexagons. That's what I would look at. I wouldn't look at the perimeter. That's an unusual ring. Look at the hexagons and which one looks aromatic. Yeah, I hope your eye took you right to here. And that looks like benzene. And we know benzene, hey, here it is again. Benzene's aromatic. So you would say, yes, it's aromatic because I found a ring that is cyclic. This ring of 6 is cyclic. Is it flat? Yeah, every atom in this ring of 6 is making a pi bond. It's sp2. Are they conjugated? Just said they have pi bonds, right? So in order to make a pi bond, they must possess a p orbital. All 6 do. So they're all conjugated. And then does it have a Huckel number? Yeah, there's 1 pi bond here, second one there, third one there. 1 line equals 2 dots. 1 bond equals 2 electrons. There's 6 pi electrons. Excellent. Let's go down here to this bottom structure. Turns out to be penicillin. Penicillin comes in many forms, and it just depends on what the other groups are out here. How many rings are in penicillin? At least 3. Yeah, so you got the benzene ring over here. You got this ring of 4, and you have this ring of 5. You got the perimeter. That might be it. There's 4 rings in here. Find one ring that's aromatic, and then we'll say penicillin is an aromatic molecule. That's how the game's played. So, yep, over here, there's a benzene ring. So, yes, penicillin is aromatic. Let me ask a different question. Is this ring of 4 an aromatic ring? Well, check your criteria. Is it a ring? Yeah, it's a ring of 4. Is it planar? I got 3 atoms looking sp3. Nobody's got a pi bond. This one has a lone pair, so that's a wild card. But this carbon has a hydrogen. There's 4 single bonds, no wild card. And this carbon has a hydrogen. It's actually on a dash bond. So this hydrogen, right? The wedge is saying this group's coming out towards us. It's implying sp3, tetrahedral geometry. Yeah, 2 of these atoms are sp3. It's probably not planar. Is it conjugated? Not if they're sp3. No, this 4-member ring is not aromatic. How about the 5-member ring? Same deal. Got too many atoms sp3. No one's got p orbital here. Maybe the nitrogen, maybe the sulfur. But you need every atom in the ring to be possess a p orbital, and they don't. This one definitely doesn't. That one doesn't. Yeah. So this part of the molecule is not aromatic, but this part over here on the left is. But that's enough to classify the entire molecule as, yes, aromatic. Let me ask you a different question. This molecule here, this part of the ring, is this an aromatic ring? At first glance, I don't think so. But if you inspect a little further, it's like, yeah, that's benzene again. What bond connects this carbon to that one? A double bond. I see it, it's right there. It doesn't matter if the line is drawn on the left side or the right side. There is a double bond between these two atoms. A double bond, yeah, that means they have a p orbital, and you get to count these two electrons. So yes, there are 6 pi electrons in this ring because this bond counts as part of this ring and part of that ring. Don't double count it. If I ask how many total pi electrons are here, and I can count that twice. 1 line equals 2 dots. That would be it. Let's count up all the pi electrons. I knew I'd mark them up, so I made copies of the molecule. So how many, I can't spell many. How many pi electrons are in pyrene? 2, 4, 6, 8, 10, 12, 14, 16. 16 pi electrons. Is that a Huckel number? No, it's not. 2, then 6, then 10, then 14, then 18. Oops, it's not. Is pyrene aromatic? Well, I'm not going to count the whole molecule and all the pi bonds. I'm going to go after one ring. So maybe I'll count that ring. Probably not my first choice, but it works. This ring is aromatic. Therefore, pyrene is aromatic. In fact, it's called a polycyclic aromatic molecule. Cool. All right. What else we got in key concepts? Part 2 for Unit 1. See if there's anything on the top right over here. Yes. Okay. We got these 4 criteria, right? Is the molecule cyclic, planar, have extended conjugation, does it have a Huckel number? That's for predicting. But as a scientist, we should have some tests, some way of deciding in the laboratory if a molecule is aromatic or not. And one such test is the NMR. So another test is stability to reagents, right? So back in the first video, we talked about benzene not reacting with Br2. Br2, elemental bromine, reacts with alkenes, carbon-carbon double bonds, but Br2 doesn't react with benzene, which has carbon-carbon double bonds. And that's because benzene is aromatic and very stable. So stable, it doesn't react with Br2 unless you add a catalyst. That's coming up later. Okay, another test, that's a chemical test with Br2. But another test is if the NMR can tell you whether or not it's aromatic. And this is how you do it. Remember the chemical shift? This is just nice color-coded chemical shift. Hey, alkanes, those hydrogens that are bound to a sp3 carbon or an alkane carbon, those hydrogens show up around 1 or 2. Hydrogens next to a ketone show up around 2, 2.5. Hydrogens next to an electronegative atom like oxygen, nitrogen, or a halide, they're 3 or 4. Here we go. Hydrogens on an sp2 carbon, an alkene, is somewhere between 5 and 6. But hydrogens on benzene on an aromatic system are farther downfield, 7 or 8. And you might be asking, well, how come? Back when we discussed NMR, we said the chemical shift is greater. The peak shows up farther to the left. 1, if it's closer to an electronegative atom, or 2, if it's closer to some pi bonds. Well, the alkene is a pi bond, but if you have an aromatic ring, there's more pi bonds. That's why it's farther down. Not quite. Here's the real reason why the chemical shift is so far downfield. The electrons in the p orbitals that are all overlapping in an aromatic system, they're free to go everywhere. In fact, pi bonds kind of act like a wire in a loop, in a coil. It's like having an electrical current, a loop of wire where electrons are free to roam throughout that coil. And you actually generate electric field and a magnetic field from these motion of these electrons. And so as the electrons move around, they actually create a magnetic field. And if you took some physics or take some physics, you'll learn about the right-hand rule. You can grab a wire and put your thumb in the direction of the current. Is current defined as positive? Forget how that right-hand rule works. And your curved fingers actually tell you the direction of the magnetic field. So here we go. I'll just trust this graph is drawn correctly. If the current, the electrons in the pi system are going counterclockwise as you look at this, then the current is producing its own magnetic field, which are following these lines here. The current produces a magnetic field that's down inside the ring, but up outside the ring, which is close to these hydrogens. The field is up out here due to the ring current. This arrow represents the magnet of the NMR instrument, the NMR spectrometer. And now if you look at the total magnetic field on this hydrogen, it's due to the external field of the spectrometer plus the ring current's magnetic field. They're pointing in the same direction. It's greater. And this greater magnetic field shifts the peak farther downfield. It's more deshielded. So the ring current is actually, due to the aromaticity, is shifting us far downfield. Well, that's a neat theory. Do we have any evidence to support it? Take a look at this crazy molecule, 18-annuline. So this is a huge ring. And it's so big, there's enough space in the middle, you can actually have hydrogens in there. So it's a ring. It's cyclic. Is it planar? Well, as you inspect every atom of the ring, everybody's sp2 because they're all involved in a double bond. If they're sp2, they have a p orbital. Yeah, they're making pi bonds. Everybody is conjugated. Well, is there a Huckel number? Let's count them and see. We got 2, 4, 6, 8, 10, 12, 14, 16, 18. 18, is that a Huckel number? 2, 6, 10, 14, 18. Yes, it is. This is aromatic. Okay, that was our prediction. Let's go in the lab and find out. Well, you put this in NMR and you see two peaks. You get a peak, so this is interesting. TMS is here at 0, and you get a peak here at -3. What? And you get another one at 9.3. Whoa, that is way downfield. Now remember, the correlation table said aromatic molecules, well, those on a 6-membered aromatic benzene ring are between 6.5 to 8. Let's look at this correlation table. This is the one you'll get on exams. So here we go. Aryl groups, arene, that's what the AR means. Most of the time we're talking about benzene. Those hydrogens 6.5 to 8. If you have a vinyl, ooh, common name, hydrogens on a alkene, they're 4.5 to 6. There's no ring current here. It's not as great. A magnetic field doesn't shift it that far downfield like the ring current does. Yeah, 6.5 to 8. 8 seems to be the limit for benzene. Well, that's an average. Remember the correlation table you have to be flexible with? So 9, that's actually the evidence that says yes, where's my pen? Yes, the molecule is aromatic. And in fact, this -3 is due to these inside hydrogens. So remember, the ring current creates a magnetic field that goes 90 degrees to the ring current itself. So inside the ring, the magnetic field is down. And now if you have hydrogens inside the ring, like you do down here, there's hydrogens, there's hydrogens inside the ring that can feel the ring current's magnetic field that's downward, the spectrometer's field is upward, and together the net magnetic field is smaller, which results in an upward shift, an upfield shift to -3. It even goes farther past TMS. That is also evidence that yes, there is a ring current. So yes, it's aromatic. Cool. So it's a great chemical test. And so you can go in the lab, put a little benzene in the NMR spectrometer. The molecule's all symmetrical. There are 6 hydrogens, but because of symmetry, they're all equivalent. And all 6 hydrogens overlap, produce a single peak. And let me look at my notes. The peak shows up as 7.37 delta, or ppm. Whatever unit you prefer for hydrogen or proton NMR. And 7.37, yep, it lies in this region. Excellent. Cyclooctatetraene, that crazy looking molecule, it's also symmetrical. All the hydrogens are equivalent. It also has a single peak, but this peak is at 5.78. Wait, 5.78. That's in the region of a vinyl hydrogen, not the region of an aromatic hydrogen. So that's the laboratory test, the evidence that says cyclooctatetraene is not aromatic. And from our previous video, we said, no, that's not aromatic. There's 8 pi electrons. That's not a Huckel number. And if this molecule were to be allowed to be flat, it would be anti-aromatic, super unstable, super reactive. Well, it turns out this molecule exists. It's stable. And it's stable because Mother Nature says, we're not going to let this be flat. We're going to bend it into a bowl shape. So the whole ring is not flat. And so it can exist. It does exist. And you can analyze it by NMR and see it's not aromatic, 5.70. Cool. All right, that's enough for now. I'll see you in the next video.